Hi everyone, this is the third and final video in my series on isolated voltage measurement. Today we're going to be utilising the Hall effect, starting off with an open loop system using this small sensor, then adapting that to become a closed loop system that should improve our accuracy, and then finally we're going to be taking a look at this commercial LEM sensor, which also utilises the Hall effect, and we're going to see if that outperforms what we can make. Let's get started. So this is a Hall effect sensor, and it should detect magnetism with 2 pins for power and then 1 as an output, and that voltage will just go up the stronger the magnetic field is that the Hall effect sensor is within. So let's start off by just plugging it into the breadboard and powering it up. Right, so that's connected up here, and it then heads to the multimeter. So if I turn this on, the datasheet says it can handle up to about 8 volts, so 5 should be fine. Turn it on here, and I'll just lock this range. There we go, we've got 1.6 volts, 1.8, 2.5. Looks pretty random to me. Let's try bringing in a magnet and see if anything happens. Yes. If I hold a magnet right next to it, the voltage goes up a bit more. And if the magnet's the other way around, it goes down. Brilliant. Right, I think those weird fluctuations are just caused by some not great connections, because now it's looking pretty stable. And basically what it should do is it should output half of the input. It's a bit like a potential divider. Half the input if there's no magnetic field, and then depending on the direction of the magnetic field, it'll either go positive or negative from that centre point. So on the most basic level, that means we can use this to transmit positive and negative voltages, and I'll show you the way we can do that now. Now here I have the output from the other channel of my power supply, which we're going to try and measure. Now voltage doesn't create a magnetic field, but current does. So what we're going to do is we're going to short the power supply, and now you can see we can use the current limit to adjust the current that's going through these wires. So I'm going to just set it straight up to 2 amps, which is unfortunately the highest that this will go. And let's see if the multimeter is going to change at all when we bring that wire close. Not really. So let's try making a stronger magnetic field from our current by adding many turns. Right, so here's a coil with many turns, and the idea with this is that every single wire that's wrapped around has its own magnetic field, and they're all going in the same direction, so then the magnetic fields add up. It also has a magnetic core inside which focuses the magnetic field and stops it from just spreading out everywhere. However, this isn't really what you want, because what you need is the Hall effect sensor to be in a gap in the core so that it gets as much magnetic field as possible, which you can see in this datasheet here, which is for an LEM current sensor, which are very sort of industry standard for DC current measurements. That's sort of what I'm trying to replicate here. And you can see they have the Hall effect sensor within the magnetic toroid. But I don't have any cores with a nice gap in, so I can't do that. This does sort of work, so like if I put the Hall effect sensor in the middle, you'll see the output of the multimeter changes when I turn it on and off. So that's with it off, on, off, on, off. And if I swap the leads around and then turn it on again, you can see it goes lower instead of higher. There is, however, a big problem with this, and that's that I'm at 2 amps, which is a lot of current, and it's barely detectable. So I'm going to try and find or make some kind of inductory thing where it doesn't have a sealed core, I'm going to call it, and the flux all comes out the end. So for example, one thing I might try is wrapping a little wire around this magnetic core, and then I can just fix the Hall effect sensor to the top there, and that should get a lot more flux. Whether it'll be enough, I'm not sure, because really we want this to be sensitive in the order of milliamps, not amps. I found this which works quite a bit better. So this is from an electric shower, and this would activate the solenoid, which would turn on and off the shower. And basically it works a lot better because there's no core in the middle of this. So you've got the terminals here, and then there's loads of windings going round. but the core is just hollow because originally there'd be a little plunger in there that would move around. And it does work quite nicely, so with 10 milliamps going through I get more voltage reading on the multimeter than I did with 2 amps just holding a wire next to it, or even with that little toroidal inductor thing I just showed. The problem with this is it's wound for 240 volts, so to get 10 milliamps to flow through, it takes 30 volts, and we're probably only going to have 5 volts. So that rules this out. Right, this is probably the best yet. Still not amazing. But what we've got here is that core I showed earlier with a load of enamelled wire wrapped around it. And then I've taped on one of the Hall effect sensors onto the end. And hopefully you'll be able to see, looking at the multimeter, if I turn up the current, ta-da, we get up to 2.8 volts on the output, which is quite nice. This does have the slight problem that it's still requiring 2 amps, which is a lot more than I'd like. But one other thing we can try to focus the field is adding another core opposite it. So it's a little hard to squeeze in, but the idea is that it should make the magnetic field a lot stronger, even if there's just a second part sitting there. And that's basically because this winding will create, there'll be a north pole at one end and a south pole at the other. And now the south can come down here, round here, up through here, ignore the little gap, and then back down, and it just means it's sort of like closing an electrical circuit. Let's see if that's made it any more sensitive. Wow, much more. That's amazing. I'll leave it at 2 amps and take this core out. Look at that, 2.8, just adding in a piece of metal, 3.3, and I can probably get it in a better position, so I'm going to try and do that now. Right, so what I've done here is I've clamped 2 cores together, and these cores have a gap in, and hopefully that gap should be just about the right size to squeeze in my Hall effect sensor. And there we go, that fits in really nicely. So let's give this a go now. Here's the 2.5 volt baseline on the output, and 2 amps in. Yeah, that's what I'm talking about. Look at that, 4.2 volts. And if I flip the leads over, we go from 2.5 down to 0.9. That's pretty much the limits of what the Hall effect sensor can output. Let's see if it's detectable at lower currents as well, because really I want this to be in sort of tens of milliamps maybe. So let's say at 50 milliamps. Yeah, we get something. That's the main thing I want. And you'll see why shortly. Now the next thing to do is once again build up a circuit that takes our input voltage and converts it to a current using an op-amp, and this time I'm also going to add a pass transistor, which I'll explain once it's done. So let's do that. Right, now I may have burnt a few components on the way, but I think I've got a working circuit now. So like usual, I'll put a schematic up on the screen that will probably make it a lot easier to follow, but we've got the same op-amp that's taking in a voltage and giving out a current, except this time the current's being multiplied by a pass transistor connected on the output, and it's getting the feedback from the emitter of that transistor, and that just means that this op-amp can then output, well, the circuit as a whole can output in excess of 1 amp, whereas the op-amp itself would probably do like maybe 10 milliamps or something. We also need a current shunt so that we can get feedback on how much current we're sending into the coil. And after the first resistor caught fire, I decided to swap it for one of these big 25 watt aluminium jobbies. So we should be able to see here now, we've got our roughly 2.5 volts idle, and then as I increase this, that voltage goes lower. And all I'd have to do is swap some wires around for it to go higher instead. The other interesting thing to look at is the current coming out of the second channel of the power supply, which you can see I've got at 12.4 volts, and that's basically because these breadboard wires I use are so thin, they've got a resistance of like 1 ohm or something, so the voltage drop across this circuit's huge, so that's just to compensate for that. But you'll see as I increase the input voltage to be measured, we go up to almost 1 amp, which is why I've got to be quite speedy when I'm taking my measurements, because otherwise everything is going to start burning and melting. Something else I just realised I forgot to mention is that you can see now we're powering the measurement side from the second channel of the power supply instead of that small 5 to 5 volt DC-DC converter, and that's because that DC-DC can only do 1 watt, and when we're pulling the full sort of almost 1 amp, that's well over 1 watt. Now later in the video I'll show a sort of commercial equivalent of this and you'll see why that's not a problem for if it's done properly. But for this example, yeah, I'm just using the power supply so that I can get the current through it that I need. But overall I'd say that's looking quite nice, so I'm going to do the measurements like I've been doing in the previous videos, add it to the Excel, and we'll see how it looks. So I'm actually really impressed by the linearity of this open loop configuration. Considering there's no feedback, I didn't think Hall effect sensors that were this cheap would be that linear. You can see it hitting a limit at 4 volt output. That's just because the circuit was drawing so much current, it was pulling the supply down, so that was about as much as it could get. For the next version, where we implement a closed loop system, I've mitigated that by not using shitty thin jumper wires. The frequency response also isn't terrible. It starts to drop off at around 100 Hz, which, yeah, it could be better, but that's an improvement over the PWM method. And this looks like it has somewhat comparable linearity to that method. So overall, even open loop Hall effect could be better. Right, well that wasn't too bad, but what I want to try now is a closed loop system. So basically I'll try and explain the principle and then I will try and implement it. Hopefully it should work a lot better than the closed loop system I tried to implement last time, because that was shocking. So the basic idea is that inside this core we have our Hall effect sensor and we've got our coil of wire. So as we put current through this coil of wire, we get a magnetic field going through the core, and the Hall effect sensor detects that. The stronger the magnetic field, the further the output of the Hall effect sensor goes from the 2.5 volts, or whatever half of the supply voltage is. But the response of the Hall effect sensor is fairly linear, as we just saw, but it's not brilliant. But what we can do is, instead of just using the output of the Hall effect sensor directly to look at how strong the magnetic field is, we can feed the output of the Hall effect sensor into another one of these circuits, but that one will be on the non-isolated side. The idea with that is that you could then add a second coil controlled by the same circuit, and the Hall effect sensor is most accurate at telling you when there's no magnetic field, because then it will just output exactly half of what you put in. So then the second version of this circuit will just try and replicate the current this circuit's making, because all it's trying to do is get the output of the Hall effect sensor to be half of the supply. So if the voltage you're trying to measure goes up, you'll get a magnetic field generated by this coil, the Hall effect sensor will give an output, and then the equivalent of this circuit over here will then replicate this current in another coil, and that should cancel it out, so then the Hall effect sensor will go back down. And basically that just means you end up with current in, current out. You can change the number of turns as well, which is quite nice. So I'm not quite sure how I'm going to do it yet, but you could have, for example, 10 turns on the input and 1,000 turns on the output, and then the output current, or the current that's driving the output side coil, would be 100 times greater than the current driving the input side coil. And this is how compensated Hall effect current sensors work. Like this LEM current sensor, which basically has you're meant to pass your wire through it, so that's a single turn on the primary, and then the secondary has, I think, 1,000, or it might be more, 1,000 turns going round a ferrite core, and this little lump is where the Hall effect sensor sits. So basically inside this you've got a core, the cable that you put through might have like 100 amps going through it. That generates a little magnetic field in the core, which the Hall effect sensor detects. Then there's some feedback and a little op-amp in here that creates a current internally on its own winding, and because that goes around 1,000 times instead of 1, you end up with 1,000 times less current on the secondary, which is then comes out on these pins. And Hall effect is the reason why I said at the start of this series current is a bit easier than voltage to measure, because those things are quite simple to make if you've got a super high current that you're measuring. But if you're trying to measure a voltage using Hall effect, you've got to convert it to a current, measure that current, then you'd create an output current if you're using a compensated system, closed loop. Then you've got to convert that current back into a voltage. And every single one of those conversions is a chance for me to mess it up. Now, a problem is that I have run out of enamelled wire, so I think what I'm probably going to do is take this winding off, chop it in half, put it back on, and then, as I said, replicate this circuit on the output, and we'll see how it does. So I'll be back when that's all done. Right, this is finally all sorted. Hopefully I can do this brilliant circuit justice with some kind of explanation. As always, I'll attach a schematic in the corner, so hopefully that will help. And let's work from input to output. So, the voltage comes in from our function generator up here. That then comes through to the two parallel 100 ohm resistors. That's for the 50 ohm termination. That means the voltage that we set actually appears here and it's not double. That was explained in a previous video. That then goes into the non-inverting input of this op-amp. The inverting input is fed by the output of this current shunt, which we'll get back to shortly. And the output feeds this pass transistor, which I've had to add heat sinks to because they get really hot. The collector of the pass transistor is just fed by the 6 volt supply, and the emitter heads over to the primary side of this sort of transformer-y inductor thing. Then the secondary heads through this 4.7 ohm high power resistor, which is a current shunt, so we can use that to measure the current, and then that heads back to ground. You can see I've swapped all the wires from these breadboard wires to these solid core ones because they've got much lower resistance, because that was the problem I was having with the previous one. And I just thought, seeing as this is the final circuit that we'll be making for this series, I might as well give it its best shot and actually put some effort into it. So back to the circuit. This op-amp has one job, and that is to get the voltage across this shunt to be the same as the input voltage. So say I'm putting 1 volt in, there should be 1 volt across the shunt, and it does that by changing the current going through the shunt. And the current going through the shunt is also going through this coil. So basically that means the current going through this coil is the input voltage divided by 4.7, because that's the shunt resistance. There's also a bit of resistance in the coil, but we'll ignore that. And I can confirm this bit does work, so if you measure the voltage across this resistor, it pretty much perfectly matches the input voltage, which means we are now controlling the current on the primary side of this inductor quite nicely. The other two parts of this inductor device are the secondary winding, which should be the same, if not very similar, number of turns to the primary, and also sandwiched in the middle we have our Hall effect sensor. The secondary is fed by an identical circuit to this, with a pass transistor, an op-amp, and a shunt resistor. The only differences are the inverting and non-inverting inputs to the op-amp. So whereas last time we fed in an input voltage and it tried to match the current to that voltage, or the voltage across the shunt it tried to match, this time we feed in half of the supply, and on the other input it gets in the output from the Hall effect sensor. So this circuit tries to keep the Hall effect sensor output at half the supply voltage, which means there's no magnetic field. And it does that by controlling the pass transistor through its output. So this circuit controls the current to keep the magnetic field at 0, even though it doesn't actually measure the current anywhere, because the current is what we want to measure. So again we have the same shunt, the same resistance, and that's what we're measuring our voltage across. So a quick example of the circuit in operation would be, we feed in 4.7 volts, 4.7 volts divided by 4.7 ohms is 1 amp, 1 amp on the primary. That creates a magnetic field of some kind of strength. This circuit then tries to cancel out that magnetic field so that the Hall effect sensor has no output. And it does that by putting a current through the secondary winding. Theoretically, that current should be exactly the same as the primary so that the magnetic fields perfectly cancel. And then by putting that current, which should be 1 amp, across a 4.7 ohm resistor, we should get 4.7 volts back on the output. At least, that's the idea. This looks quite cool. I think this is probably going to be my thumbnail. Now all that's left to do is run through the usual tests. So let's have a look at how it performs. Comparing the linearity to the open loop setup, it does look better overall. There's a weird kink at the bottom that kind of throws it off a bit. But if you look, it's almost exactly 5 volts out when it's 5 volts in, 4 out when it's 4 in. It's a little bit below when you get to 3. 2 it's pretty much bang on. 1 it's a bit high because of, as I say, there's this weird knee at the bottom. And when it comes to frequency response, I'm not entirely sure how, but it seems like switching to this closed loop configuration has improved that by almost 2 orders of magnitude. You'll notice the roll-off on this is very steep, and that's because that's not actually how the amplitude dropped off. I just set it to 0 because I'll show you in a minute, but the output went a bit weird starting above about 10 kilohertz. It started to distort basically. And I'm pretty certain that's because we're using magnetism, which means, especially when we've got a load of wire coiled around a magnetic core, we've made an inductor, and inductors block AC. So the higher frequency we try and send through the system is just going to get attenuated and weird stuff's going to happen. So I think we get a really weird, distorted waveform, and I think that's probably to do with a load of resonance in the system, different frequencies interacting. So I think because this Hall effect system inherently uses inductance, that's going to limit the upper frequency of it. So let's take a look at how the output goes a bit weird at high frequencies because of the fact that this is inductors we're talking about. This is at 10 kilohertz and we're getting a nice sine wave coming out of the circuit. If I increase up to 20 kilohertz, you can see we're starting to get slightly pointy bottoms on our sine. And increasing up to 50 goes even weirder. So it's sort of siney, but there's a lot of weird rippling going on. Right now I'm in high res mode. If I go into normal, yeah, some weird stuff going on there. Then, if I go up to 100 kilohertz, you'll see why I stopped at that point. Because this is not my input. Ugh. And that's just because inductors and stuff. Now there's quite a few things on this circuit that aren't very good that you'd fix in a commercial unit. So for example, the fact that this transformer requires sort of in the order of amps to get a good reading coming out of the Hall effect sensor, that's not very good, so you'd probably add more turns. Then there's the problem that it does also act like a transformer. I just called it a transformer, but it shouldn't be one. That's another thing where if you made a core specifically for this, you could eliminate issues like that. And that leads us on to what I've been teasing for most of this series, which is a proper Hall effect sensor. This is a real voltage transducer made by the all-conquering LEM, who have just a complete monopoly in the voltage and current transducer market. This particular one also makes use of the Hall effect, although it requires a much lower current to operate. So it's rated for a maximum input current of 14 milliamps with a nominal of 10 milliamps. So the idea is that you put a resistor in series with the input, as you can see in this example schematic given in the datasheet, and then it will draw a small current, 10 milliamps, from your supply. From that current, it can then use exactly the same principles that we've just applied for our circuit, except done properly, and it can produce an output current that's 2.5 times the input current. So if you have the nominal 10 milliamps coming into the input, then you'll have 25 milliamps coming out of the output. It's also bipolar, so you give it a plus minus 10 volt supply and it can give you plus minus 25, 30 milliamp output. Then all you have to do is put that output through a shunt of your choice, and it'll give you an output voltage that's completely proportional to the input. And this is super linear, DC, AC, pulsed. So let's pop this in a breadboard and see how it does. So here's the finished circuit with the LEM transducer. You can see they just make everything so simple. The only reason that this circuit's at all complicated is because I've tried to match the 50 ohm output impedance of the function generator with this weird combination of resistors. Because the input of these LEM sensors is around 250 ohms, but not perfect. They're intended to measure much higher voltages, so then whether they're 250 or 230, it doesn't really matter because you'll have multiple thousand ohms in series with it. Whereas in this case, I've had to put resistors in parallel to bring the impedance down to the 50 ohms the function generator expects. But you can see I've got both outputs of my power supply set to 12 volts. That creates a bipolar supply, so you've got minus 12 volts on this side, plus 12 volts on that side. That then feeds the secondary side of this transducer, and the primary side, yeah, is just fed by a current that's derived from the voltage we're trying to measure. Then the output has 3 pins, you've got positive and negative, and then there's an output which just outputs the current that it's using for the secondary winding of the internal magnetic stuff. We can pop that across a resistor like this, that's our shunt, and the voltage across that is the voltage on the input basically. and you can select the value of that shunt to get a bigger voltage or smaller voltage depending on what you want. And here we can already see it's going to be a very strong performer because 5 volts, 5 volts, 4, 4, 3, 3, 2, 2, 1, 1. Then you've got 0 volts out, 0 volts in, and where this really comes into its own is the fact that it can go negative. So if we go to, what's this, -1 volt, -1, -2, -2, -3, -3, it's crazy. The only thing I'm not completely certain on is what its bandwidth performance will be like, but I imagine it will be very good. So let's find out. So here's the same linearity plot from earlier, this time with the LEM sensor added, and you can see, well, probably the first thing you notice is that the closed loop one is actually quite close. But yeah, the LEM one is just unbeatable. It outputs the correct voltage at pretty much every input. The only reason there appears to be an offset at the top here is because my function generator doesn't output a perfect 5 volts. But yeah, it's almost a perfect straight line, really nice. And as I say, the closed loop that we've made isn't that far off. And overall, I think ours is actually better, especially when you take into account the frequency response. Look at this, the LEM starts to drop off before it even reaches 100 Hz. Oof. Whereas our closed loop system that we've made can go flat response beyond 10 kHz, which is really nice. So I'm not sure why it's so poor. My guess would be that because the LEM is so much more sensitive, being able to run at 1 or 2 milliamps, it's probably got a huge amount of turns on the core inside. That would make the inductance very high, which would block high frequency AC. It is odd though, because the datasheet does say high bandwidth, but apparently not. And here's a plot showing the best that we made from each video. The PWM optical with its lovely linear output, the optical analog with its interesting quadratic curve, and the closed loop Hall effect, which is almost linear, but has that annoying knee at the bottom that gives it a bit of an offset. And now let's add in the LEM sensor to see how that compares. And you can see overall, the open loop optical system is definitely the least linear, but the PWM isn't too far off, and the Hall effect I think might be even closer than the PWM, which is a big surprise. Then looking at the frequency response of the best system from each video, you've got the PWM optical with its shocking roll-off that, even at 10 Hz you're losing amplitude, pretty bad. Then you can see the optical analog and the Hall effect. They're quite interesting because the optical analog begins to roll off sooner, whereas the Hall effect kept a pretty nice output amplitude until it just sort of almost very suddenly started getting all weird and distorted, which is why it has such a steep drop-off. But both of them have pretty high bandwidths. I'm pretty certain that the optical method has way higher potential than either of the other two though, which is why if I'm going to do a follow-up video, it will be on that. Because the PWM's bandwidth is inherently limited by the switching frequency you use, and the Hall effect you're limited by the fact it's an inductor. So I think the reason why the bandwidth of what we've made is so much better than the LEM one is because we're running at really high current. It's a really inefficient system, but because we're running at higher currents, we've got lower inductances, and that attenuates higher frequencies a bit less. I'm pretty sure that's why we can run at much higher frequencies than the LEM. Whereas for the optical, what is there to limit the bandwidth? Nothing really. You can change the intensity of an LED about as fast as you want. The datasheet of that really nice Vichet dual optocouple thing, that said 1 MHz, so I'm very tempted to get one of those. Don't forget to go back and like that video, because if it hits 50 likes within a month, I will buy one. And adding in the LEM, you can see it's actually quite interesting. It's pretty much identical to the PWM optical, just an order of magnitude higher frequency, but a roll-off that starts attenuating at 100 Hz is pretty poor. And you can see how the optical and closed-loop Hall effect that we made are just miles better. So that's it for this series of videos on isolated voltage measurement. I hope you've enjoyed and found it interesting. I probably will do a follow-up at some point if I can get hold of that Vichet optocoupler, because I think that can probably beat this LEM module quite handily. Looking at the bandwidth, it's amazing how poor the bandwidth is of this really. Other than that, I've got quite a lot of plans for future videos. I think the next one is probably going to be some kind of clickbaity capacitor thing because I want more subs. Speaking of which, don't forget to subscribe, like the video, and until next time, have a good one.